Hello, my name is John Capobianco, and this is part two of a two-part series in consensus artificial intelligence using various infrastructure components such as Kubernetes to build multiple AI systems that will come together into consensus. So each is going to give their individual opinionated answer. We're going to take those collected answers and send them back to each AI with a new prompt, a new instruction set, instructing it to come to consensus with all of the other answers. And we can do this iteratively. We're going to do it twice to come to a final consensus. Now, the first part talked about how to get your home working machine up and running with Windows, WSL2, Ubuntu, Docker Desktop, finally Kubernetes in the form of Minikube, and how to set up access to your GPU. This video is going to focus on code, two forms of code. The infrastructure as code, IAC, meaning the YAML files and the commands that we're going to use to build servers, to build infrastructure. Then the code within some of this infrastructure to do the consensus-based AI. So this part two in the series is going to build on part one, and we're going to really focus on the code and the commands. Now that we've installed Kubernetes and have access to our GPU, how do we then actually build a Kubernetes cluster with pods and a network and containers and a load balancer and a reverse proxy? So we're going to do all that today. Thank you for joining me. I hope you enjoyed part one. Part two is going to really explore infrastructure as code and proper Python code. All right, so let's take another look at this again from the beginning. And here is the abstraction layers. We have my Windows 11 home computer with Linux via WSL2, Ubuntu, Docker Desktop, integrated with WSL2, and Kubernetes via Minikube integrated with Docker Desktop. All of these have access to the GPU. And what we're going to be focusing on today is this layer here. First, building our Ollama pods, then our code, our Streamlit code, and then finally how to connect it all together and present it through a reverse proxy. Now, I might not go in that order. I'll probably look at the reverse proxy earlier in the description. But basically, we have these infrastructure as code microservices in the form of containers that are running Ollama and a container with NGINX configurations and a container with my Streamlit Python code, the front end. Okay, so if we go up to the conceptual idea here, what I want is a front end where people can upload a packet capture and in the background perform retrieval-augmented generation and let them ask questions about that packet capture. I want to use multiple models in this retrieval chain, so 4 separate retrieval chains, to come to individual answers. Once I have those individual answers, I'm going to restructure the prompt into a consensus algorithm and provide all of those answers to each of the AI, LLMs, SLMs one more time. And we're going to do that iteratively a third time to come to a final consensus. So the idea here is that if I get a good answer, where's my freehand drawing here? If I get a good answer from a few of these LLMs and maybe a bad answer here, when we come to final consensus, these LLMs are going to consider that 3 of the 4 are very similar in answers or have come to the same conclusions, and hopefully filter out that bad answer. Now, ultimately, I guess I could pick a singular so-called best AI and come to a single best answer. But for now, I'm going to have each of the AIs provide their own individual final conclusions through this process. So how do we transform these two kind of ideas here into a working Kubernetes pod? Cluster, I should say. Well, let's take a look at it. So I am using VS Code as my IDE, and if we go to the extensions, you're going to want a few extensions here, in particular the Kubernetes extension and likely the Docker desktop connection. You're going to want these things so that way in your tray here on the left, we have Kubernetes access. And you can see right now I have my default and my Docker desktop, and there's no Minikube because I haven't created it yet. And in my Docker, you can see that there's no containers, for example. All right, so first things first. Let's bring up our Minikube server. And then we're going to look at some, actually before we do that, let's go back to the tabs I have open on purpose. Right, so you're going to want Docker Desktop. You're going to want to integrate that with WSL. We're using Kubernetes to scale and manage all of these containerized apps in the form of Minikube, which will run inside of Docker. Now, why I've decided to use Minikube is, again, I can get access to my GPU through Minikube, whereas the Kubernetes for Docker Desktop integration does not have access to the GPU. We're going to be using, I call it kubectl. I could be wrong, but kubectl for the command line tool, primarily to drive our infrastructure as code. We're going to be using this to apply configurations to the Kubernetes control plane. All right, so we're setting up the control plane for Kubernetes via the kubectl command. I'm going to be using NGINX for a reverse proxy. I only have one host and I have multiple services running on different ports so that they're unique, but I need to tie them all together through the web browser so the user can just visit, localhost/packet-kate to get access to the front end. And then when I make my API calls to the other Kubernetes pods, my Ollama pods, I needed a way to provide access to those ports over my local host. So this is my reverse proxy, and I will show you the configuration. This is free and open source as well. We're going to be using Ollama and different models from Ollama inside of different pods. Okay, as our LLM host, as our server for the large language model, in our case, the small language models. We're going to be using LangChain to build the Retrieval-Augmented Generation system in concert with Streamlit for the front end. Okay, and so let's take a look here. I don't know that there's much more to draw, but what we want to do is have a user. I can't even, let me undo those, that's terrible. Let's say, a user, again, visit localhost /packet-kate. Can I make that any bigger yet? So I want them to visit this URL in their browser. The user is going to upload a PCAP, yikes, PCAP, my mouse is not behaving, and then chat with it. right? Ask questions about the PCAP. In this URL. That's basically all I want to happen. And then the answers come back and we do this process that we've described already up here in the corner. All of this is behind the scenes through the Kubernetes. All right, so I think I'm done with Excalidraw. Let's actually get into some of this. So the first thing I need to do is bring up my Minikube. So we're going to turn Minikube on and give it, right, using the driver Docker, using our Docker driver and our container runtime Docker, giving it access to all GPUs, and I'm giving it access to, 16 CPUs and 10 gigs of memory. Now this usually doesn't take very long to boot up Minikube, and now Minikube's up and running. Now what I normally do next is go into Minikube SSH, and do a Docker ls, Docker image ls, and we can see the images that we have inside of our Minikube. Now, we're going to be using, if I go back, I should have kept that image open. Give me 1 second. Now, again, here, if I zoom in, we're going to need 3 different images. The Ollama image, the NGINX image, and our code, our Docker container version of this packet chat code. All right, so we'll come back to this file, Ollama pod. But if we look at Ollama pod, we can see the image names here. What I'm going to do is I'm going to pull these images, Docker image pull, the Ollama image, because there's a follow-up command here that says image pull policy, if not present. So if it's present, then don't download it from the internet. Now, because I have n number of Ollama pods, in this case 4, but it could be 16 or 28 or whatever, instead of downloading this image that many times, we can just SSH into our Minikube and download the image ahead of time, and then use this flag, image pull policy, inside of our pod definition to say, if not present. So this shaves quite a bit of time off of the build process when we actually apply our Ollama pod Kubernetes configuration. Remember, we haven't applied anything yet. We haven't built a cluster or anything yet. We're just SSHing into the Minikube shell and pre-populating some images. So the other image I'm going to populate is my is the NGINX latest image. And then my personal image. Now these might take a bit of time, so I'm going to talk through, while it downloads my image, I'll then backtrack and talk about how I've built my image. So let me get another terminal open here while this downloads in the background, and we'll get NGINX downloaded next. Docker pull NGINX, and this is rather tiny, so this won't take very long. And then my own container for the packet Kate implementation. And that's going to take a couple minutes because it's a few gigabits in size. So how do I build this file? This has nothing to do with Kubernetes. We're talking about my Docker image. So I have a packet Kate's Python script, and I have a startup script that will do the Streamlit run, and then that packet kate Python script as a Streamlit application. There's a file known as a Docker file that I'm building from NVIDIA CUDA 12.5 development Ubuntu. So this is an Ubuntu image. However, it has the CUDA framework built into it. And if you watch the previous video, we talk about installing CUDA. What CUDA is essentially, think of it as a driver to give GPU access. So I want to have an Ubuntu container that has access to the GPU, and then I'm going to install certain packages that are required, such as Python 3 and all of the LangChain packages that I need, ChromaDB, jQuery, Streamlit, the T-Shark application, Python Shark, the request library, and the .env to load the .env file. I'm going to talk a little bit more about the .env file. So I have this Docker file, I have my packet kates. There is a Docker build command. If you bear with me here, hopefully it's still in my buffer, or we can look it up. Here we go. So what you're going to do is do a Docker build -t, your name on Docker Hub, and the name and latest tag, period, to pick up the Docker file and my packet file and my script and everything. Once that's built locally, we're going to push it up to the cloud with a Docker push command and our tag, which is what the Minikube is downloading from the cloud now in the background. Okay? So that's a quick crash course on how we're going to take the Python script and a Docker file and build a container with all of the required components needed for my application to run inside of that container. Now, while we have some time, if you go to the README file, the first thing we need to do is ensure that the NVIDIA device plugin is enabled for our Minikube. So we can make another terminal. Now it's going to throw an error and say that it's already installed, but it's still a good practice to make sure that this device plugin is present in your Minikube setup. The next thing that I do is to create a secret generic OpenAI API key secret from my .env file. All right, so I'm going to copy and paste this command, and it's going to say that there's a secret created successfully. Okay, this is how we can handle publicly publishing code and storing code on GitHub for Kubernetes that it needs an env file. So for example, I'm using OpenAI's public system to do my embeddings. I'm using their model for my embeddings in this RAG document here, right? So when RAG needs embeddings, I'm using OpenAI. So I need to use a key for that, but I don't want to store my key on GitHub, obviously. So you can see there's a gitignore file that includes .env. Gitignore is respected by the Docker build command. So when I did the Docker build, it did not include the environment file. And for us to, properly use this code with our own secret in the .env file, we need to create a secret adding a secret to the Kubernetes control plane from our .env file. All right. So Minikube is getting close to being ready to go. Let's look at the files. There's a simple file that we're going to make. It's only 12 lines of YAML. That is a load balancer service listening on port 80. So when I visit localhost 80 / something, this Kubernetes instance is going to be listening on that port and doing round robin load balancing. Now I only have I don't necessarily need the load balancing capability. I'm using this to expose port 80 on my local host. We'll get into the pod file next, but let's look at the NGINX config. Now this is not, right, so in my pods, I have an NGINX config here, an NGINX pod that we'll talk about in a bit, but I want to pre-configure that pod. So before I bring up the pod, I want to build this NGINX config, this NGINX conf file. So when I bring up my pod and the NGINX pod gets created, it has these settings to start doing reverse proxy. So I'm going to describe my 4 Ollama servers listening on, the default Ollama ports 11.4.34, so 5, 6, and 9, whatever ports we have here. And then my actual packet kate service the user visits. Listen on 80. And now there's a little bit of rewrite here. What happens is I need the API to answer on /generate. So it's kind of funky, but I had to do this rewrite to get this to work from an API call at the back end. So we have the services listening and the backend services listening. So when my Python code makes an API call to one of the LLMs, and we'll get back to this in a bit here, right? Localhost backend model generate, right? That line of code corresponds with these listening services from the reverse proxies perspective, okay? So our Minikube is done. We can exit, and we're going to clear. So we followed our README. We've created the connection to our GPU. We've created our secret. We're going to go ahead and create our front end, and we're going to go ahead and apply our NGINX config. And the next thing is the actual pod YAML file. So let me minimize these first, and we'll just get into what we're building here, because it's not that bad, right? So this is a pod. I'm calling it Ollama pod with a label of Ollama. And then I have different containers. So let's look at the tiny llama container. The image is the Ollama image. Pull policy is if it's not present. We'll skip the command. It's listening on 11.4.34. We have our environment that we've set up. So the path to the models, the URL where the API host is, and a keep alive. Now, the keep alive is important. By default, and it makes sense, and for resource preservation, if I make one API call to Ollama, it's going to load a multi-gigabit model, answer the question, but then keep it there for up to 2 minutes in memory so we don't have to load it again and again. And for most purposes, that is a great efficiency advantage. However, I'm going to answer the question with Tiny Llama, and then I want to answer the question with Phi3. But if Tiny Llama is still hogging the GPU, then Phi3 is not going to have the resources to answer it. So we set a value of 0 to keep alive so that it immediately tears down after it's done its answer. All right? We're going to allocate some resources here a little bit of memory and some CPU to this container. Now, because it's Ollama, I found that I don't need to explicitly allocate GPU to this pod. And in fact, that actually causes some problems. So let Ollama discover the GPU for these Ollama pods. Now let's look at, say, Phi3. How do I get Phi3 into this Ollama container after I've built it? Well, I'm using a shell command to first start Ollama, sleep for 20 seconds, and then pull the Phi3 model and tail out to dev null. Print some stuff on the screen while all this is happening. So it's going to boot up. Ollama's going to discover the GPU. We're going to let it settle for 20 seconds. And then we're going to download the Phi3 model. And that's it. It's ready to go. This pod will be up and running and hosting Phi3 in an Ubuntu image with CUDA and GPU access. This is what we mean by infrastructure as code. With just this little bit of YAML here, we're going to instruct Kubernetes to build a full-blown pod on our network with listening ports that we can access through our reverse proxy. Now, the only difference with my code is a different port number, and I use the standard port number for Streamlit, 8501. But for this pod, I am actually explicitly allocating GPU to this pod. Otherwise, you'll get an error that the GPU is unavailable when you turn this system on. So we want to explicitly let this pod have access to the GPU. And then the NGINX, it's going to be, on port 80 with that service. And we're going to mount the NGINX config file that we've already applied. Okay, so let's go ahead and apply our Ollama pods. And the first thing that I usually do immediately is go into my Kubernetes extension, find my Minikube, go to workloads, and go to pods. And you can see I have an Ollama pod that is green and healthy with 6 running containers inside of it. My 4 Ollama containers, my NGINX reverse proxy, and my Streamlit application. Now we can explore this a little bit more, but there's not too much else to see. We just want to make sure that our pods are running under workloads. We can see that we have our Ollama pod here under our nodes Minikube. Okay, and we have all this description about what's going on in the YAML files. If I want to see the logs, we can run this command and see the logs. So let's look at the packet Kate container. And it's up and ready and happy. And we'll come back to this one. If I check my Ollama Tiny Llama, it's already started to download the Tiny Llama model. But you can see that we've discovered the RTX 2060. Right, so this Kubernetes pod, if we go all the way back to our original diagram here, we've established this connection between the Ollama pod and our GPU, and we have the evidence of that here in the pod logs. So unfortunately, I am literally downloading, and let's just check our other pods. So that was Tiny Llama, we have Phi3, we have Llama 3, and we have Mistral. These are all going to take some time to download. However, let's look at one more thing before we break and come back. Right now, on localhost packet Kate, I should be able to visit the page based on the logs we just looked at, right? So if I look at the packet Kate log, it should be listening on 8501 and then hosted behind the reverse proxy to this packet Kate URL. Well, let's do one command here, and we're going to get our Ollama service. Remember that Ollama service we set up? This file here, our load balancer. Let's take a look at this service. We have our cluster IP, but our external IP is still pending. So we've bound 80 to our internal port here, but we're still pending for an external IP. That's why I can't reach it. So we're going to run a Minikube tunnel command, which is going to prompt us for our sudo root password, right? And we need to keep this terminal alive for this tunnel to be accessible. But now if we run that command again, we can see we've bound it to our external host. And now I can visit my front end. And we're up and running in just a few commands. All of that infrastructure as code is ready and running. We're just waiting for the models to download from the internet. It's about 20 gigs of data over 4 models. However, our front end is now accessible. It's just taking a second here. Something's freezing up. Our front end is going to be accessible here in a second once my memory unlocks. There we go. There we go. Okay. So we have to have this tunnel open. And now we are ready to access our front end. Once the models have finished downloading, so Tiny Llama is almost done because it's only 700 megabits. I do want to show you the logs once it has completed downloading and we know that the actual Ollama servers are ready. But I'm going to pause this video and I'll come back once these models have finished downloading. Thank you. Okay, so we are back, and if we look at the logs for our servers, Tiny Llama, we should see success. And we actually see the size of the model not in terms of parameters, but actual disk, right? So Phi 3 is about 2.2 gigs. Llama 3 is 4.7 gigs. Mistral's 4.1 gigs. So there's not a one-to-one ratio based on the size and the quality of the model. Let's not misunderstand that. However, some of these models are double the parameters, double the size. So we should expect to get, hopefully, better results from something like Llama 3 or Mistral over Tiny Llama. Now, I'm using these as placeholders to show you this idea of consensus. We could substitute ChatGPT or Gemini or Claude for paid services for really high quality answers, but I'm trying to explore the world of free and open source models and see if this consensus approach can help us improve the output. So how do I get this front end listening on a port? We've already talked about all of the infrastructure as code that goes into this. Let's look at code as code. And I'm going to zoom in just a little bit here. So let me collapse these things. I meant to collapse them all ahead of time. But this will actually help me explain what's going on if we have everything collapsed. And then we'll get into the purpose of each function and how everything works. Now in total, it's only 327 lines of code, and that includes probably 50 lines of prompts. So some of the things that we're going to need are requests and JSON and operating system and UID. I use subprocess to do the T-shark work and Streamlit. There is a bunch of LangChain code we need, including the Ollama integration, the conversational retrieval chain and buffer memory for RAG, Chroma for the vector store, the JSON loader to load the JSON version of the packet capture, a semantic chunker to break up that JSON, and the OpenAI embeddings model that I'm going to use in the cloud. I have .env to handle the environment variable. We've already talked about that. And this is how I can expose it in my code, that key as an environment variable. So I have a couple message classes up here that are just for the history and the Streamlit presentation of the messages. We're going to load the embeddings model from the cloud as a function here, so we can go get the embeddings. And then I have this pre-pended information that I'm going to add in front of any user prompt. So if the user says, what is the source and destination IP, I'm adding this in front of that prompt to help maximize the efficiency of the prompt. So some prompt engineering work here. We have a class that basically handles the RAG function. So we're going to load the JSON. We're going to split it into chunks. We're going to store it in Chroma. We're going to set up some memory. And then we're going to send our requests to one of the NGINX servers for each model that we have with this data prompt. The model, the prompt, and a keep alive of 0. We're going to initialize our chains. And then we're going to have our chat approach and our chat interface, where we loop over these different models. Now here comes the consensus part. Hello, esteemed models. I'm seeking your collective expertise to reach a consensus on the following question. Below are the individual responses from each model and all of the results from each of the original model's answers. Please review these responses carefully and provide a reasoned summary that attempts to align and synthesize the various varied perspectives. Consider the strengths and weaknesses of each response and aim to identify common themes of points of agreement. Then we have our final consensus prompts, which is kind of similar, right? Thank you for your thoughtful responses. I'm asking you to further refine to come to a final consensus on this question. Here are the preliminary consensus answers so far. Please evaluate these summaries, identify the most compelling arguments, work toward a unified, well-supported final answer. Your final response should integrate the best elements of each perspective and resolve any remaining discrepancies. Keep the original question in mind and do your best to come up with most agreed upon the answers to that original question. All right? Now I have my model selection page and I have my PCAP to JSON function and my upload and convert PCAP page and then my chat. Hi, I thought it would be a good time for us to take a break. As you can see, I'm in a different shirt. It's a different hairstyle. It's a different day altogether. I've spent the better part of 2 or 3 days in between where I cut the last video and where we are today for various improvements and reasons. One, I wasn't getting great answers with the mix of LLMs that I was using. So I've replaced some of these LLMs and we'll explore the LLMs that I've landed on before we move ahead. The next thing is, I was really inspecting the data we were sending the PCAP information from. These small language models are much more sensitive to any data we put inside of our prompt, inside of our context window. So something like data from a PCAP, which when you look at it after you transform it into JSON, it's just a bunch of hex data. UDP dot data, and then it's a huge string of just hex information in the packet capture. Well, this information was, in my opinion, poisoning some of the prompts because it's this huge string of just hex information. It's just garbage text. Wasting tokens, wasting context window size, confusing the LLMs. So we'll look at some of the code that I've implemented to strip this data out. So it's more or less the header information only and none of the payload information. Nothing of value is lost here. It's just hex data. So it's funny, in the pursuit of making this project work, I've actually found ways to improve my overall PCAP translation process, which I'm going to trickle into other projects. So let's go back to the code. Let's take another look at this, okay? And we'll talk about the new models and we'll talk about some of the Python refinements. Okay, so as you can see, I have successfully pulled the new models down. And if we look at our NGINX and our pod configuration, the 4 models that I've landed on are now, Gemma 2 from Google, Qwen from Alibaba, Llama 3 from Meta, and Mistral from Mistral. So those are the 4 models that have been pulled down, right? Ollama pull Mistral into these pods. And they're all listening and ready to answer now. Now, in terms of the packet capture refinements, let me find them. So first of all, when I'm doing my original jQuery schema, I'm going to delete any .data layers. Now this, when I upload a single PCAP, it usually splits the headers and the data into 2 different chunks, 2 different vectors. So let's just go ahead right up front when we load the JSON and drop any data. That's a pretty big and significant improvement, generally speaking. Now the next thing that we're going to do when we load, where did it go? 1 second here. When we load, so that's loading the JSON. There's another spot here where we're going to further refine the data. And I just have to find it in the code right here. So when we do our PCAP to JSON conversion, there's these deep inner layers of UDP payload or TCP payload. So what I'm doing is I'm removing these layers and then I'm reassembling the JSON. This is right when we convert the PCAP. So in 2 different spots, I'm dropping data. Now, let's take a look at these results because it's quite astounding and quite remarkable and really does hammer home the point of consensus. So I've uploaded a PCAP, and let me show you the PCAP I've uploaded to be very transparent and clear here. So this is the PCAP with a source of 192.168.2.61 and a destination of 169.30. It's UDP with a port number, of a random port number going to port 9000. So I've uploaded this PCAP and I've asked it, what are the source and destination IP addresses in this packet capture? So here are the original answers. Llama 3 gets it right. Mistral gets it right, and even includes the port number information. Qwen gets 1 out of 2 correct. It gets the destination IP correct, but it hallucinates on the source IP as a MAC address. So, and then our Gemma 2 response is also correct. So 3 out of 4 are correct on all information, right? 4 out of 4 are correct on the source, and 3 out of 4 are correct on the destination. Now, it's hard to take any single one of these at face value and so-called trust it. Do you trust an individual answer? Well, what if this was the individual answer with Qwen? I don't, that's obviously a MAC address, not an IP address. Now, this is where the consensus comes in. So the consensus response from Llama 3, after reviewing the individual responses from each model, I've identified some common themes and areas to agreement to help summarize their collective expertise. Right? All models agree that that's the source, while only 3 agree that that's the destination, with an outlier. Right? It talks about the strengths and weaknesses, but it comes to a reasoned summary. Now, this is Llama 3. That's the source, that's the destination. And we're going to consider Qwen's response to be an outlier, given it's a MAC address. Now, this is the consensus from Mistral. In all the responses, the consensus response, right, in the destination IP is this, and the source IP is this. There's a discrepancy, but the majority of the responses, it's most likely these 2 addresses. Qwen sort of hallucinates a little bit more here, but comes to the correct answer. And then Gemma 2 comes to a similar consensus amongst the algorithms that the source IP is this and the destination IP is that. So they all come to the correct conclusion on the first layer, and then we do a final consensus, and everyone's final consensus agrees on the correct source and destination IP. Okay? Now let's try this with a different packet, and let's ask a more generalized question about, like, what can you tell me about this packet? So let's grab a DHCP flow, and I'll show you what this DHCP flow looks like, just so you get an understanding, and we have some anchors as to what's the, true values here. So this is a broadcast trying to, discover, offer, request, acknowledge. A standard DHCP flow. So let's see if the AI can recognize this DHCP flow and what it can tell me about it. Right? So let's just say, what can you tell me about this packet capture? Now, what's interesting is, if I launch my task manager and we watch the resources here, we're going to see the GPU spike as the GPU takes on each of these models to respond. So we can see it peaking here, my GPU. And if I did the logs of, let's say, Gemma 2 or Llama 3, we can see that it's entered the GPU here in the logs. And it's actually trying to do that inference for us. So based on what I can gather, right, here's some source and destination MAC addresses, the IP addresses, DHCP. They, both packets it captures indicate that they are DHCP related. So that's what it can gather from these packet captures. And it all is accurate, valid information. Llama 3 is very, very close to some of the public models, as you can see. Every piece of information is correct here. So let's see what Mistral says. This is a packet capture of a DHCP message. Indicates that it's happening on a private message, that it's DHCP here. So this is all pretty good stuff. Qwen appears to be related to a DHCP transaction. Okay, very good as well. So 3 out of 3 so far all seem to know that it's DHCP related. Each of them is able to get different source and destination MAC addresses and IP addresses. We're just waiting for the final answer here to come in from Llama, Mistral, Qwen. It looks like we're waiting on Gemma 2. And as we can see, Gemma 2, it's in the GPU right now. And if we check our resources, we can see that it's still in the GPU here. So we'll just wait for Gemma's response. And then the next pass will be consensus. And it's interesting because they should all sort of tend to agree on the different pieces of information here. Each of the models so far does indicate the correct information about a DHCP packet, and each of them gleans different perspectives and information. So I'm very interested to see what happens once Gemma 2 answers, and then we actually get into the consensus algorithm, and that they should come together to know this 4-packet DHCP flow. So we're just waiting again. Now, the Gemma 2 model is the largest of the models that we're running here so far. So this doesn't surprise me that it takes a little longer to do the inference and the answer. It's 6.7 gig in size. And we can see that it's using my NVIDIA 2060 here. So we're just waiting for that answer from Gemma. What I'm going to do is pause and come back once we have all of the consensus answers. All right, stay tuned. Okay, so we have all of our responses, including Gemma from Google. Now, Gemma is a larger model, so it does take a little bit more time, as you saw. But, right, let's start analyzing this DHCP packet. So it knows it's DHCP. We see the process here: discover, offer, request, acknowledgement, analyzing the capture further. All kinds of information. So now we get to the consensus. And let me zoom this in here. The consensus from Ollama, that it's a DHCP packet capture analysis between two devices, a client with the MAC and the IP, and the server with the MAC and the IP. The key observations, the DHCP process, additional insights, the tools for capture analysis, and now we get Mistral's consensus. DHCP transaction, right? So reinforcing our trust, reinforcing our confidence in the answer from the AI, because it's not just one AI, it's multiple AIs working together to come to consensus that this is a DHCP packet capture analysis, and all of the insights that it can expose and provide us, working amongst themselves to throw out any outliers and to reinforce each other's answers, really is powerful. So we've seen a single packet capture, we've seen a DHCP packet capture, all through this consensus approach through Kubernetes. So let's go all the way back to the start here, right? Can we upload a PCAP? We perform retrieval-augmented generation using OpenAI, ChromaDB, and then 4 different retrieval chains using, I don't want to write them all down, but in this case, Qwen, Llama 3, Mistral, and Gemma 2 from Google. Each of them answers individually, and we come to a consensus. And if there's an outlier, like we saw with the MAC address instead of a source IP address, we're going to consensusly throw that out democratically and come to a final consensus where all of them provide the best answer via the democratic consensus. Now, to go all the way back to the hardware, how this works, and I'm just using a RTX 2060 here from NVIDIA. This is not a high-end card. This is an old graphics card from my gaming machine that, through various levels of abstraction, Windows 11, WSL2, Ubuntu, Docker Desktop, Kubernetes via Minikube, and the Minikube NVIDIA plugin, individual Ollama pods that all have access to the GPU, and a Streamlit application with a retrieval-augmented generation LangChain using an NGINX reverse proxy to orchestrate all of this through a simple browser interface. So this has been a two-part video series. First, we focused on the infrastructure as code, building servers, building actual Ubuntu Linux hosts using nothing but YAML files and kubectl, Kubernetes control plane commands. We had a reverse proxy in NGINX, and we have a front-end load balancer from Kubernetes as a service. We have 4 Ollama pods. These are NVIDIA CUDA Ubuntu images with Ollama installed, where we tell it to pull a particular model per pod, and a Streamlit LangChain front end where we can upload a packet, ask questions, perform the LangChain RAG process using OpenAI for embeddings and Chroma for the vector store to do conversational retrieval chain. Now, we filtered out quite a bit from the PCAP. We're throwing away any data. We're throwing away any UDP data, any TCP data, because it's just a huge long string of hex that can lead to hallucinations, that uses tokens unnecessarily, that ruins your prompt. So using some magic with Python, when the user uploads their PCAP, we're stripping out data. And when we JSON query it, we're going to throw out any data as well. I think this is remarkable. I personally think this is a breakthrough, and I'd like you to share this with people. I'd like more and more people to start thinking about this, not just AI singularly, but a bunch of AIs working together to bring that confidence level up, bring the level of trust up. Say, well, if all 5 of these, all 4 of these LLMs agree that that's a DHCP flow, it's a DHCP flow. So, the code is on GitHub, and if you have any questions or comments or improvements, please let me know. I'm going to be experimenting more with this, and I'm going to be incorporating my improvements into Selector's Packet Copilot over the next few days. Happy holidays, happy new year. We'll see you again in 2025.